Well, look, I hope you've actually been reading the text. Now, what I want to do here is really have a look at characteristics, okay? Now, my focus here, okay, is going to be on the common, what's referred to as the common emitter configuration. So it's the common emitter configuration that we'll look at. And let's just draw a diagram of that for a second, or at least a diagram of the transistor. All right, once again, here is the transistor. All right. Remember, I said to you before, we'll look at Npn transistors. Okay. Now, we've got our collector current IC. We've got our collector emitter voltage VCE between the collector and the emitter. We've got our base current IB. And between the base and the emitter, we're going to have the voltage VBE. That's between the base and the emitter. Now, this is referred to as a common emitter configuration. One way to look at that is this base side is really going to be an input side when we're talking about amplifiers. So our signal, etc., is going to be on this side of the circuit over here. And then the output side of the circuit is over here. And so really the emitter is common between, as it were, input and output. All right. Now, what we want to look at in relation to characteristics, okay, we've got really two sets of characteristics. We've got an input characteristic, that is on the input side here, which is a plot of IB versus VBE. And then on the output side over here, we've got a plot of IC versus VCE. All right, now let's first of all look at the input characteristic. So this is the input characteristic. That's our plot of IB versus VBE. And guess what we're seeing? What we're seeing basically is a diode type of curve, and we will use the second approximation where this is 0.7. Okay, so for normally biased transistors, when we're using our transistors in amplifier configurations, not as switches, but when we're using them in amplifier configurations, okay, we will assume here, as far as the input characteristics are concerned, that basically the voltage VBE is 0.7. Okay. Now let's have a look at the output characteristics. Now look, in the lab you may be building a circuit really similar to this one here. So let me just quickly draw that circuit. Here we have our transistor, NPN. Here's, if you like, the common. Let's put a resistor in here, which we'll call RC. Let's come over here with a voltage source, like so. And then on the input side, or the base side, let's put a resistor there, which we'll call RB. And let's come over here and put another voltage source like this. Okay? All right, now we want to use this circuit really to measure, as it were, the output characteristics. So we're looking, if you like, at output characteristics, which is really a plot of what? It's going to be a plot of this collector current versus the collector emitter voltage. That's what it's going to be. All right, so let's plot this. Here we go. Here's the graph. That is IC, the collector current, and this is our axis for the collector emitter voltage, VCE. All right, now let's imagine doing this. How are we going to do this, if you like, in the lab? Well, what we're going to do is we're going to fix this voltage here. That's this voltage source for to establish a base current. We're going to fix this. This is a fixed resistor here. So all of this is fixed. So the base current here is fixed. Now we can determine what that base current is. We'll be doing a lot of this later. It's just a simple loop around that circuit where this voltage between here and here is our 0.7. Okay, so that base current is now fixed. Okay, now over here on this side of the circuit, what we're going to do effectively is vary this voltage here. Remember, our purpose with this circuit is to try to plot this characteristic, this output characteristic for the transistor. Okay, so we'll set this value, this voltage, to a certain value. We'll measure IC, we'll measure VCE, and we'll get a point. Okay, so we'll plot that point on the graph. Okay, then we'll change this. Maybe we increase this. We'll now measure the IC and the VCE, and we'll get another point. And if we continue on, what we'll eventually trace out as a series of points is a curve that really looks like this. Okay, so this is a curve that really looks like this. Now, for our purposes, we'll assume basically this line here of our curve is parallel to the VCE axis. In reality, it's not quite parallel, but for our purposes, we'll assume that it's pretty much parallel to the VCE axis. Okay, so that's a characteristic, that's an output characteristic, a plot of IC versus VCE for that transistor when we held the base current to a certain value. Okay, now I could label the value that we'd put for the base current on here, and if I did that, I might say, oh well, look, let's say that was IB1 for that base current. That's the value of base current. Okay, remember, it's a plot of IC versus VCE having established or fixed a given base current. In this case, we said that base current is IB1. Now, if I were to change that base current, let's say I made it a bigger base current, how would I do that? Maybe I increase this voltage source, make it a bit bigger, all right, and then hold it, fix it. I've now got a larger base current flowing, okay? And then I repeat this whole procedure here, okay? I set this to a certain value, I measure IC, I measure VCE, and I plot it on the graph. Maybe I get a point sitting right here. Then I increase this VCE, I increase this voltage here, okay? If I increase this voltage here, okay, I measure IC, I measure VCE, and I plot that point on the graph like so. And then once again, increase this further, measure the IC, measure the VCE, and plot. What I'll find is I get another characteristic curve looking like this, okay? Now this is the characteristic curve, okay? This one here, it's a plot of IC versus VCE, having fixed the base current at a new value, a higher value, which we could say might be IB2. Once again, I could basically change the base current. I could make this base current a bigger value and really do the same thing again. And what I end up getting really is a series of these curves, IC versus VCE. Now, this region here, this vertical rise region here, is referred to as the saturation region. And then this straight line section here, these lines, as it were, are parallel to this VCE axis. This is really called the active region between here and here. Okay, and that's something we need to focus on. All right, so those are the characteristics. The input characteristics, looking much like a diode. Second approximation is what we'll use, and then the output characteristics being a set of curves like this. And that's the circuit that you might consider using in order to plot these characteristics. Okay? Okay, let's talk now about the need to actually define an operating point and what this operating point really is all about, okay? All right, first of all, we're going to make the assumption, okay, as far as the input is concerned, we're going to assume that really VBE is equal to 0.7, okay? All right, now, what about this operating point? So if we look at the operating point, how do we find it? All right, now, if I've established, for example, a certain VBB here and a certain RB, I've got a certain base current flowing in that circuit. Or I could hold that fixed, that's a fixed resistor there, I've got a certain base current flowing. I'm going to be on a certain characteristic curve. So look, if I come over here for a second, and I'll just draw those characteristics for a second. Okay, here I've got my plot. This is the output characteristic again. A plot of what IC really versus VCE. Okay, now I'm going to be on one of these characteristic curves, and that's established by what this base current really is. All right, now what we want to do is find out the operating point. What is the actual IC flowing? what is the actual VCE in this circuit. All right, so what we're going to do is we're really going to plot the load line on this output characteristic. Now, how do we get the load line? Well, the load line is nothing more than just taking a loop, all right? So if I do this, the voltage between here and here, I'm going up. We could label that, of course, that's VCE plus minus. So what have I got? I've got VCE. Okay, the voltage across this resistor. All right, now look at the way the collector current is flowing. The collector current is flowing this way. This is IC, so it's what? From a plus to a minus. So I'm going up again, so I'll say that's plus IC times RC. It's Ohm's law. Okay, and then I've got this drop here, which is my power supply. I've called it VCC. All right, so minus VCC all equals 0. All it is a simple loop equation. That voltage plus that voltage plus that voltage is equal to 0. So we've summed the voltages around the loop. Okay, if I'm rising in potential, I call it positive. If I'm falling in potential, I call it negative. Okay, I need to re-express this as IC as some function of VCE. All right, so what am I going to do with that? I'm going to take this to the other side. I'm going to take this to the other side. I'm going to divide by RC. I want you to go away and try that as well. You could even pause at this point and just try that and see if you come up with the answer I'm just about to write down. Okay, so IC would really be equal to a minus VCE divided by RC plus VCC, that's the power supply, this guy here, divided by RC. Please verify that you can do this from this simple loop equation here. Now, in order to plot this load line, I really need 2 points. So what are the 2 points? Okay, I'll choose simple ones. I'll choose the case where IC is 0 and find the VCE. Okay, so IC equals 0. What is VCE? Well, VCE would be what? That's 0, that goes to the other side. VCE is the power supply, which is VCC. Okay. All right, the other point would be what? Make VCE 0. So if VCE is equal to 0, then what is IC? IC then becomes simply the power supply, which is VCC, divided by the resistance in the circuit, which is RC. So those are my 2 points, which I can now plot here. Okay, this point here, of course, would be what? VCC, so that's my VCC point. This point here would correspond to what? It would correspond to this current, which would be what? VCC divided by RC. I could join these two together like so, and there is my load line. Now, I've established a base current in this circuit due to what? This voltage source here and my choice of resistor. So let us assume for a minute that the characteristic curve that I happen to be on is really this one right here. Okay, that's the characteristic curve that we are currently on. Okay, and this corresponds, let's say, to a certain base current, which I will call IBQ. All right, that's by choice of that voltage there and that resistor. So if I come down to the voltage axis, that would be the actual VCE between here and here. We could call that VCEQ. And of course, if I go across to the current axis here, this would be the actual IC. We could call that ICQ. And this point here then is referred to as that operating point. That is the operating point. Okay? Now I want you to take, a little break with this. Okay? Have a think about this. Look at the circuit again. Think about what I'm saying here in terms of the characteristic curve you are on. It's a function of what that base current is. That establishes the characteristic curve you happen to be on. And then look at the output here, the output part of the circuit here. Draw a loop around there, sum these voltages around the loop, write down your load line equation, and then see if you can plot that on the graph like I've done here, and then establish where the operating point is. Now, what I want you to think about, okay, this is really the end of the second part, okay, and we'll pick up this again in the third part. But what I want you to think about is, okay, what if I were to add, in series with this DC source here, what if I were to add, for example, a little sinusoid in there? a little voltage source, okay, a little sine wave, okay, and maybe its peak value is what, half a volt. So it's going up half a volt, down half a volt, up half a volt, down half a volt. What is that little source going to do to this circuit? Okay, and you might consider an instant in time. Consider the case maybe where this sinusoid that would be placed here is plus half a volt. That means this voltage here is what? It's bigger now, isn't it? It's a larger voltage. It's this voltage VBB plus the half a volt. What does that mean on the base current? It means that this base current's bigger. If this base current is bigger, okay, what does that mean by way of what is happening? Larger base current will put me onto a different characteristic curve, a different IC VCE characteristic curve, maybe one that's higher up here. And then consider the case when this little voltage source, this sinusoid here, is minus half a volt. Now I've got VBB plus a minus half a volt. I've now got a voltage between here and here, which is actually less than VBB. I've got less base current flowing. That puts me on a characteristic curve maybe down here somewhere. Now I want you to think about that a little bit as you break from this particular section.